Welcome everyone for the 10th lecture of Introduction to Astronomy and Astrophysics course on ISSS platform. Today we will cover rest of exoplanet hunt, and then if the time permits we will introduce what are the galaxy and about galaxies what we would learn in this course. So yesterday our lecture was about the exoplanet hunt. We have read that there are four types of exoplanet, broadly four types of exoplanet, such as terrestrial exoplanet, super Earth-like exoplanet. Another is the Neptune-like exoplanet and the gas giant-like exoplanet. As the name suggests, the Earth-like exoplanets are the smaller planets which are made of rocks or metal, and some of these exoplanets are believed to be uh, host some atmosphere that is can persist the habitability, and another planets the super earth planet, another type. They are typically terrestrial planet or a rocky planet, but they are more massive than earth but lighter than the Neptune, the outer planet of our solar system. There are also Neptune like planet in our galaxy, you can say. uh, these Neptune-like planets are the similar size of Neptune and Uranus. They are mainly made of hydrogen or helium dominated atmosphere they have. Some Another type of planets are the gas giant. Those are the size of Saturn or the Jupiter, two biggest planet of our solar system. So they in this gas giant include are typically very near to the host star, and sometimes we call them or refer them hot Jupiter. So these were four basic type of exoplanet, and also we introduced that there are different techniques of planet detection, such as the transit radial velocity method, direct imaging, microlensing, and astrometry. These four methods we discussed broadly, and also we introduced the website of this exoplanet website by NASA. And as for the last week, there was about 5834 confirmed exoplanet in this as per this website, and the newest discovery is gets updated within few weeks or few days here in this website. If you want to be want to teach someone about the exoplanet, this website will be a great tool to start with for your own. And the next step we just learned, I am just recapping yesterday's lecture. Yes, so here, so the method of the radial velocity method, as this GIF is showing you, that your star and the planets are rotating about the common center of mass. As the star is moving away from you, you will see that there is redshift, and as it is closer to coming closer to you, then you will see the blue shift. So if you can detect such redshift and blue shift from the starlight or the stellar spectra, you can detect that there is some planet that is making the host star being rotated. And the next method we discussed is the transit method. This is the most simplest method. When the planet comes in front of the host star, some brightness of the host star will be dimmed, and this periodic brightness variation can help you to detect that there is a planet in the orbiting the host star. And the next step we learned that about the Kepler mission yesterday, which mainly used the transit light curve plot of transit light curve to detect the newer planet. The next method was the astrometry method, in which the abnormal rotation of the or the abnormal shift of the star that hosts in planet is detected. So this method need great resolution to differentiate between the host star and the field star's motion. The next method is the micro lensing method. We discussed that suppose here is a very distant star which has have very high brightness. When some closer star uh, makes an apparent motion in this direction, you can see that there will be a brightness rise in the distant star, and you can plot this distant brightness change with the close star's motion, with the close star's apparent motion or the time go as is going on. So now if the nearer star contains a planet, then there will be high mass. The light from the distant star will be bent due to higher mass. So there will be, the planet will cause a small blip on this graph, brightness time graph. So this method is known as the micro lensing or the gravitational micro lensing, for the, you can say that correctly. Here was a bright star, very distant bright star from you. So when a in front of a star, nearer star is crossing in between you and the distant star, you will see that there is a blip in the light versus time graph. You can see here in the figure very clearly. The next method is the direct imaging method, where you image the exoplanet itself. And if you can image such method, also you can check what is the path the exoplanet is moving around the host star. But for this exoplanet, generally these exoplanets are much more dimmer than the star, about 10 to the power 8 to 10 to the power 9 times dimmer than the host star. So you need very high contrast to detect the exoplanet from the exoplanet using this direct imaging technique. So for the direct, it has been seen that the planets mainly emit in the infrared. There are, so if you want to do direct imaging of planet, you have to look at the stars which are infrared poor star, such as the white dwarf or the brown dwarf, so that you can build some high amount of contrast between the flux of the exoplanet and the host star. And also another way is to doing the if to doing the coronagraphy, that is you block the light from the host star. This will increase the whole image sensitivity or the field of view sensitivity. Then you can detect the planet itself, directly detect the planet itself. Sorry. Atmosphere of the planet, here also you can the planet spectra can be taken, and the chemical composition of planet can be told from the the spectra. So until now, mainly the transit method is one of the best way we have seen that for planet detection, because it has detected high number of planet till now. It has detected about 74% of detected planet are detected by around 74% of the planets which has been detected so far has been detected using the transit method. And the radial velocity method is also another way, and about 20% of detected planet are detected using this method. Microlensing and imaging, this are growing field. This kind of detection by microlensing or imaging has been going on since 2010, that era. So there are small number of planets are detected with these two methods. So I listed here a few exoplanet missions, but for this lecture I will not discuss any of it. So now this is one summary what we learned till now with the previous day's lecture and with the today's lecture. So the planet star system or this two body planet star system orbit around a common center of mass. That center of mass sometimes known as the barycenter. So the stars have a orbital velocity. Due to Doppler effect, this motion of star shifts the spectral line. If the star is coming towards you, then the spectra will be blue shifted, and if the star is going away from you, then the spectra will be red shifted. So if this blue shift or red shift have to be measured in if you are using the radial velocity method. Radial velocity method has some inherent bias. It detects the massive planets which are very closer to the star. So the radial velocity can detect only the hot Jupiter-like planets, as they provide the largest stellar velocities and they have the large gravitational pull due to gravity as they are near. But the radius of the planet itself cannot be measured with the radial velocity method. This is one must known drawback of this radial velocity method. The next method we learned in this course is the transit method. So when the planet passes in front of its host star, the host star's brightness will dim for some amount of time, or that is the transit time. If you can see the subsequent dim bright profile in the luminosity versus time or the light curve known as periodic light curve, then you can confirm that there is a planet that is present with the star. This method is the transit method. When you combine both these two methods, that is the radial velocity and the transit method, you can detect the full parameters of the system, that is the mass of the planet, mass of the host star, size of the planet, orbital inclination, orbital shape or the major axis orbital shape or the length of major axis of orbit, those parameters. This all four are the must known parameter for any exoplanet. Preliminary analysis, we had a preliminary discussion of how the duration and the brightness drop for the equatorial transit of planet is derived. I have not discussed that today. And how the maximum orbit inclination for a transit time occur was discussed yesterday. It was not very clearly discussed, but in the there are slides. If you want to know more, you can just check that. And also there was some discussion about astrometric method, where you have the sensitivity to detect the abrupt motion of the planet host star compared to other nearby stars. And there were other method was gravitational lensing, where the brightness curve of the distant bright star show a small blip around blip due to the passage of nearby planet star system. And for the direct imaging method, as we discussed, you have to omit the light from the host star by any way, some clever way you can say, and this will increase the contrast of your field and you can detect the planet which is very fainter than your host star. So now one of the main question in your mind will be how the planets form. There are few things those has been observed in our solar system. So they are defining characteristics to be explained by the theory of the solar system formation. So these characteristics are as follows. All the planetary orbits lie in the equatorial plane of the sun. Planetary orbits are detected to be nearly circular. Planets in the sun revolve in the same direction. This is called as the poke red, east to west direction. Planetary composition varies roughly with distance from sun. That is, the inner planets are more dense and metal rich and outer planets are hydrogen rich. And in the language of here in the language of astronomy or astrophysics, you can say The hydrogen and helium are non-metal, and after that there are all the elements are metal. Sun and all other planets except Venus and Uranus rotate on their axis in the same direction. This is known as prograde. So Sun and all planets except Venus and Uranus rotate on their axis in the same direction. This is known as prograde. Planet and the satellite systems resemble the solar system. Planet satellite systems resemble the solar system thing. Planets have much more angular momentum than Sun. There were the previous evolutionary theories which were proposed for the planet formation failed to explain this. We will sometime may discuss this in our lecture. How the Earth formed? This was our first question. Why was begin the study the sky or the cosmic objects? So in the 18th century, the theory attributed to both Pierre Laplace and the Immanuel Kant was that solar system formed by the gravitational collapse of a large, roughly spherical rotating cloud of gas and dust, and the angular momentum conservation in the plane of rotation leads to the formation of disks plus a protostar system. So what is the cloud collapse? Here is just a small picture of the cloud collapse. That is, the first thing was the cloud starts to collapse under its own gravity. In the second part, the central condensation form and the rotation speed increases as the cloud contracts and flattens around the disks. In the next stage, the protostar has been formed and it is surrounded by a disk of gas and dust. Observationally, the evidence has been found for this collapse from cloud and the formation of the solar system or any planet star system. Here is one such observation with the ALMA telescope. This was the image for a protoplanetary disk around a very young star, that is the star HL Tauri. You can see the fine details until 2014 had never been seen before the planet forming. This image was seen in 2014, and you can see the planet is forming around a young star with rings and gap. Here is the link from where I have taken this picture. If you wish to study about this more thing about ALMA observation of planetary disks, rings and gap, and from that there the planet formation itself, you can visit this link. So ALMA is a millimeter telescope which studies the universe at 35 to 950 gigahertz that regime. In this image was made in 2014 by ALMA observation of a very young star, that star HL Tauri. You can see there is something is getting collapsing and that is forming rings and gap, and that's forming ring and gap. So rings, you can see here that those are rings, and between two rings there are gaps. And here is the bright central star, very young star HL Tauri at the center. It is believed that in the ring and gaps, for rings and gaps, the planets get formed. Here are more observational evidence with the higher resolution ALMA observation. This is an ALMA image of a protoplanetary disk around young sun-like star known as TW Hyde. It reveals a tantalizing gap at the same distance from the star as the Earth is from the sun. Here are additional concentric light and dark feature you can see, and which features you can see, and it represents other planet forming region, which represents other planet forming regions out to the text. Here is the link for this image. These are all public link and made using very low level language. So if you can want to learn more about such observation and why such observation, what is the main findings of this observation, you can visit those links. So what is the role of mass and the angular momentum? We have seen that the collapse from a single cloud of gas explain many solar system feature, especially the features which are the coplanar feature, prograde feature. So we have seen that the two planets such as Venus and Uranus do not prograde in the solar system, in our solar system. But all the other planets move in the same direction of the sun, and the orbit of the planets and the sun are coplanar. It is believed that the redistribution of angular momentum and mass is required for solar system formation. Let's consider the rotational angular momentum of the sun versus the orbital angular momentum of the planets. So this rotational angular momentum can be written as the product of I of sun and I omega, and I of sun can be written as a 2 by 5 mr square, and the planet's angular momentum can be written as mvr. I omega I sun, you know, that is the moment of inertia of any body which is rotating, and as you can imagine sun as a sphere, then this is 255 m omega mr square is the moment of inertia, that is just come from formula, and v and r are the velocity of the planet, and smaller is the velocity of the planet, m is the mass of the planet. Now you can compare mass and the angular momentum in the solar system with this formula. So it has been seen that the basic properties of planets in the solar system here. The basic properties of planet in the solar system is given, such as the semi-major axis, the eccentricity E, the orbital inclination I, the mass mp of the planet, and the mean radius rp. If you can just using the formula, you can just find the mass, the angular momentum of the planet, and make this kind of plot. And if you plot this kind of thing, you can see at the outer planets such as Saturn or the Jupiter, the angular momentum is higher, mass is higher. The mass is closely linked with the angular momentum. And the most massive planet, Jupiter, has highest mass, Saturn has highest mass. Highest mass. The most massive planets such as Jupiter has the highest angular momentum, and the Saturn has the second highest angular momentum, but the Sun have the lower angular momentum from the this highest mass planet. Sun contains 99.8% of mass in your solar system, but less than 1% of angular momentum the Sun have. So one of the main question in your mind can be why the Sun have lowest angular momentum despite of being the highest or the most massive object of the solar system. So it is believed that the sum of the angular momentum from the Sun transported out from the center, so mass can fall in during the initial cloud collapse. The mass flows to r is equals to 0, that is the center of the solar system, the position of Sun. The angular momentum is carried by a negligible fraction of mass flows towards r is equals to infinity. As the mass flows inward, the disk stretches outward. Here is the just typical picture of this angular momentum transport from the sun to the disks of the solar system. Uh, most of the angular momentum distribution is this. The sun has the has highest mass, but lower angular momentum than the highest mass planet, and this highest mass planet has the greater angular momentum. It is believed that the some amount of sun's angular momentum gets transported to the outer uh, uh, disks as the disk stretches. So remainder of angular momentum is lost after sun starts fusion. The sun enters the T-Tauri phase of intense jet and the stellar wind emission. This sweeps out the remaining gas and dust in and out its protoplanetary disks. So this leaves the protoplanets. Here is one such example of the T-Tauri star. T-Tauri stars are the very young star which have the jets, wind and disks. All features in that system can be seen. They are known as the pre-main sequence star. They are those stage of star where the angular momentum transportation is still ongoing to the disks. So you can see there is jet, winds and disks. This kind of some feature that is emerging from the system is clearly seen. Some example of the T-Tauri stars are shown here in this slide. Some T-Tauri stars are detected in infrared, that are this IDAS ID at the infrared detected source, and this other T-Tauri stars name has been given. So what is the theory of the planet formation? It is believed that planets are formed from the protoplanetary disks. We need to convert cloud and dust into planets. So there are different phases of planet formation. We have just divided those phases in three different epoch or three different phases. One have to keep in mind that the composition of the planets changes in between inner and the outer solar system. This is explained by the conditions in the protoplanetary disks and the snow line or the frost line. You can see what is the snow line or the frost line. I will not discuss here in this lecture. Hotter and the closer planets we see. As near to the star, the planets are hotter. As the kinetic energy from the collapse radiates away, this is because kinetic energy from the collapse radiated away different materials from a different zone. Three main formation phases and the time scale: from dust to planetesimal, from planetesimal to the planetary embryos, and shaping the orbits and the system composition. So before going to the planet's formation, we should recap what we learned. So it is believed that as the kinetic energy from the collapse radiates away, different materials form in the different zones, and the composition between the planet changes from the inner of our solar system to outer of our solar system. Inner planets, you can see they are the rocky planet or the terrestrial planets, or the outer planets are the gas giant or the gas contain the gas. They do not have the solid rocks. And the three formation phases of the planets are the dust to planetesimal formation, then planetesimal to planet embryo formation, then is the shaping of planetary orbits and the composition of the system. So this phase 1 lasts for around 25,000 years. That is the dust to planetesimal. In this phase, the grains of material condenses out of cooling protoplanetary disks, and this material gets segregated by temperature. Inner solar systems get the iron, nickel, alloy, silicates, and oxides, and the outer solar system objects get dominated by icy condensates of water, ammonia, and methane. So, there are experimental evidence for planetesimal formation. A realistic experiment to characterize the dust coagulation in protoplanetary disks must be done in the microgravity. This is a result of some lab test where the experiments has been done to the where the experiment has been done to show the dust growth over 20 seconds using a Rexus ballistic rocket program. Here is the link from where this slide is taken, has been given. So in the lab, generally the test are being done for how from dust the planetesimal forms under the microgravity. So what are the this is one of the key thing about where the planetary scientists with the knowledge of the dust or the motion of dust, who have the knowledge of dust uh, or for me from the who has knowledge of the those kind of thing, study how the planets form from different kind of material. Yes. Yes. So this was the test for this was a result of a lab test. The next stage is the formation. This step is the formation from the planetesimal from dust. So, what if someone asks you, what is planetesimal? Planetesimal is a small 1 to 10 micrometer grain that's just to aggregate via the weak bonding of gravity, and they build up they built up to 10 to 100 of meter. It is still hard to explain the growth size per centimeter size due to fragmentation and drift. So there are some models which discuss about the fragmentation of chunks of denser disks via the gravitational collapse. I will not discuss this. I will only tell you to focus on what is the planetesimal. So planetesimals are the small 1 to 100 micrometer objects or the grainy object that get collapsed or collapsed due to the weak gravitational or weak bonding. So they are built up with the tens to 100 of meter. In the phase 2, this phase 2 lasts about 10 to the power 6 years. Yes, there is a typo here. The phase 2 lasts for about 10 to the power 6 years. In this phase, the from planetesimal to planetary embryos get formed. Here the gravity takes over. So yes, the planetesimals are not by gravity itself. Here is the very small role of gravity. Mainly the other forces take here. The people who study about the grains or grainy structure generally do some the realistic lab experiment to see how the planetesimals grow from dust, or some planetesimal like object can grow from the dust. And the next these planetesimals are formed via weak bonding. Gravity has very less role here. From the second step onwards, the gravity takes over. The planetesimals of few kilometers size start to attract each other and get collided. This is a runaway growth process of largest planetesimal in each radial zone. This process is called the gravitational focusing. This process has some good term known as gravitational focusing. This growth can occur by the pebble accretion. This builds the planetary embryo, which is roughly 10 to the power 23 kg. Here is also a typo. This slide has many typo. I will try you to correct. I will tell you to try correct the typos, because from this scene you can just guess where is the typo. This is your job to just check the typo, because you know the roughly the scales of the planets, mass of the planet itself. So yes, this was my fault, of course. So this planetary embryos are about 10 to the power 23 kg of mass and about 1 astronomical unit size. 2 10 to the power 6 kg mass or 10 AU size. This is the mass and size range of the planetary embryos, which get formed from the planetesimal from the gravitational attraction of planetesimals, you can say. In the phase 3, this is the least rapid stage, or this stage take many years. That is, the stages are about 10 to the power 8 years. This shapes the orbits and the system composition. 100 moon to Mars size planetary embryos coalescence and or they're ejected to leave the current inner solar system in stable orbits. Massive outer planetary embryos sweep up ices from the planetary nebulae or the core from using the core accretion and become gas giant, and then accretes in own debris disks and the moon system. Sometimes stellar wind from the young sun or the young star sweeps the nebular material from the solar star planetary object system, and now this lifts the system, the whole system, what we see today today. So we'll learn about 3 key steps of planet formation. The first step, this first step is the most rapid. This first stage is the most rapid stage. So here the grains of material condensate out to the cooling condensate out of cooling protoplanetary disks. So the key thing for this phase is the material gets condensate and they form planetesimal or the very small objects of around 1 kilometer or 2 kilometer. Now you can see that this phase take less years in the least years in the for the planet formation scenario. So this phase for any Earth-like planet, it takes around 25,000 years. So one thing we must know that why this kind of stage happens so fast, and what kind of bonding this grains have so that they can form the planetesimals. To understand that, some people or some scientists, you can say some scientists, yes, we will just tell that some people study how these grains get attracted and form the small objects, and why this process is going going very rapidly. So this was a test where there was you can see first test for the Rex's ballistic rocket program, where they done some protoplanetary disk formation test in the microgravity condition to see how the dust form planetesimals. This planetesimals is a small object within few kilometer, and they are met with the small grainy object that are with the small grains. These small grains are about 1 to 100 micrometer in size, and due to weak bonding they condense and form the planetesimal object, and these planetesimals are less than 1 kilometer or you can say 10 to 100 meter correctly. We must Keep in mind that it is still hard to explain the growth pulse to the centimeter size from grain to planetesimal formation. As there are two processes such as the fragmentation and drift. So some models invoke the fragmentation of chunks of the denser disks also. In the second phase, the planetesimal form the planetary embryo. These planetary embryos are about 10 to the power 3 kg to 10 to the power 26 kg mass and about 1 AU to 10 U size. In this planetary sesamals to the planetary embryo formation, all the interaction, all the main interaction is the gravity. All the main interaction due to gravity. So growth also occur by two processes, that is known as the pebble accretion and another is the gravitational focusing. But the largest planetesimals just grow, largest planetesimals just collide and they grow bigger size. And in the phase 3, this phase 3 does for 10 to the power 8 years. It shapes the orbits and the system composition. About 100 moon to Mars sized planetary embryos coalesce and they are ejected to live the current inner solar system stable orbits. Massive outer planetary embryo sweeps off ices from the planetary nebulae by the process that is known as the core accretion, and this massive outer planetary embryos goes larger and become the gas giant. And sometimes you can see that this it is believed that this massive outer planetary embryos create their own debris disks and the moon system. And you can if you remember correctly that there was for the Saturn, Jupiter, there were high number of moons there, around 60-70 moons they have. So this creates its own debris disks and moon form, and in this own debris disks there are moon formation. The last step or the last key step is the stellar wind from the young sun sweeps the remaining nebular material from the solar system and lifts what we see today. There is the between we and the Mars. We do not see the planetesimals are moving. So this is because the stellar winds from the young sun have swept the remaining the nebular materials that were between us and the Mars during the the solar system formation, and this leaves what we see today. So here is the short summary of the phase 1 and the phase 2. For the phase 1 is the accretion of centimeter sized particles. Grains clump together. These particles are known as grains. They are of 1 to 100 micrometer size. This clumps together and form some centimeter then kilometer size object. Less than a kilometer size object. Those are known as the planetesimals. So first thing is the accretion of centimeter size particles, and then the second stage is the physical conditions on the kilometer scale, so that the kilometer scale particle can persist and form the planetesimals. Now gravitational accretion takes over over the whole thing in the system, and this gravitational accretion on 100 to 10 to 100 kilometer size, and these planetesimals form just merge due to their own gravity, and then as the planetesimal merge they form the protoplanets, and the protoplanets, which are of the protoplanets of 100 to 1000 kilometer mass, kilometer size. The size is of this protoplanet, I guess. Yes, I have to check that. Just give me some time. In the next class, I will tell that. Yes. Another thing what you should just check that similar to their when you plot the planet mass versus separation, you will see that the radial velocity method, you can in the transit there are two methods, this is the transit and the radial velocity. You detect two kind of planets using radial velocity and transit, but they are similar to Jupiter but very close to the parent star. You will detect a large number of planets. These planets are known as the hot Jupiter. One of the main key question is how the hot Jupiters form closer to the parent star. One theory is the thing that the hot Jupiters form at the largest separation, that is the beyond the slow line and the migrate inward. So the question will be how. This discussion is about the hot Jupiter and the planet migration. Hot Jupiters are the objects which are detected to have or the exoplanets, those are detected to have the higher mass, but they are very closer. Very means around less than 0.1 AU, 0.1 AU or 0.2 AU astronomical unit. That is 10 times closer than us, the closer than Sun. If there is some planet which is 10 times closer than the Sun and mass of the Jupiter or or the 10 times Jupiter or 5 times Jupiter, those kind of planets. Now one of the main question is the how that kind of planets form in some planetary system. One theory is that the hot Jupiters form at large separation beyond the snow line and migrate inward. There are two types of migration. One is known as migration 1 and another is known as migration 2. So migration 1, here the planets, that's the terrestrial-like planets, generate spiral web in the disks that give rise to the non-symmetric torques. The outer one is stronger than the inner one and the planet loses angular momentum. So the planet migrates towards the sun. And the second type of migration, here the massive planets like the Jupiter can open gaps and migrate inward as the gap moves inward due to the viscosity lower than the type 1. Hot Jupiter, it is believed that hot Jupiter needs to be migrated via type 2 before the disk is cleared. We will not discuss migration thing very deeply. We will just give details that the hot Jupiters are believed to be migrated. Hot Jupiters, those are found near the host star, are believed to be migrated from the outer of the planetary believed to be formed at the outer of the solar system and migrated by some process. This two processes has been hypothesized, such as the type 1 migration and type 2 migration, and these processes are due to the angular momentum of the planet itself, how the disks the mixed morphology in the planet star or system. That in that sense, this migration depends. One of the key or the main motivation for us to study exoplanet is to detect if we have alien in the universe. Do we have any signature of life? Yes, this slide also have many typos. For this, the main thing to study why we are we alone in the universe, we generally study exoplanet, or that is the main beauty of studying exoplanet, to detect if there is some condition of the Habitability condition. This introduces this idea of the habitable zone for the potential life-bearing planets. In this subsequent slides, we will see how the expression is derived for the equilibrium temperature of the planet under the assumption that the star is radiating away as a black body, and we explain why the low mass stars are favorable host of life-bearing planet than the high mass stars. The high mass stars means OB, A, those kind of stars. Compared to those kind of stars, the K-type or M-type stars are more favorable to host the life. And we will discuss how the greenhouse effect happens and what is its implication for the surface temperature of the planet. This discussion will be very qualitative discussion, and then we will show how the retention of planetary atmosphere depends on the ratio between the thermal equilibrium of velocity and the escape velocity. So the first idea is about the idea of the Goldilocks zones. So what is the Goldilocks zone? This is the region of a solar system in which has the necessary conditions for life to emerge and flourish. We assume that we require a terrestrial planet for life, and this planet will support the liquid water. For this, we will require those conditions that are neither too hot or too cold, but right for the water to be liquid. We will discuss hierarchy of conditions. The first condition is the host star. Then the second condition is the temperature of planets. In the subsequent slide, we will discuss what are the other conditions for the planet to be a member of Goldilocks zone. So, what is about host stars? Properties of host stars are crucial in determining whether there is potentially habitable planets are present in a system. There are three key factors. One is the luminosity of the star, another is the lifetime of the stars, and another is the spectrum of the star. The second criteria is the temperature of planet. For life, we require liquid water at the surface of planet. The temperature of the planet is very critical to be critical, as if very high temperature, the water will go vapor, and very cold temperature, there will be no water, the life-saving water or the liquid water. All the water will be in form of ice. We can consider example of Earth. Heat energy in from the sun balances the Earth's thermal emission. To heat a planet, if the total power or that is falling from the sun or the star is luminosity L star, the total power can be written as a function of the planet's radius, the orbit of the planet around sun, or the orbit of the planet star system, and the albedo, that is known as albedo, that is reflectivity of the planet, that is what amount of reflectivity is the measure of what amount of light is falling from the star and what amount of what amount of light is falling on the planet from the star, and what albedo is the measure what amount of light is falling on the planet versus what amount of light is reflecting away from the planet. We will assume that the star and the planet behave like the black body, that is the sigma t to the power 4 into 4 pi r square is the power out, and the luminosity of the star is related to the radius of the star, surface temperature of the sun, star or the sun. So by equating this power in and the power out, one can get a measure of the temperature of planet as a function of the star's temperature radius of the star, AP, that is the planetary orbit or the planetary orbit distance, and the albedo of the planet. TP is known as the equilibrium temperature of the planet. For stellar habitable zone, the region around a star where the conditions allow the liquid water to exist. For Earth-like planet with the atmospheric pressure is equals to 1 atmospheric pressure, the habitable zone must simply defined as the when the planet temperature Tp is within 273 to 373 Kelvin. Here is one comparison where the you can plot the distance from star versus the stellar mass, and here for the water body, the line where the water body where the water freezes and the line where the water stay in the liquid phase. So here are the different stellar type. You can see the OBFGKM, and they have the different temperature. And if we consider their radius order also, and we can see that the inner and the outer radius habitable zone, that is the known as the ecosphere, varies with the spectral type of stars. The main sequence and the dwarf stars are tabulated. Very narrow very narrow range for there is very narrow range for the habitable zone for this different spectral type of stars. Another key thing is the stellar lifetime. That is evidence of what simple life on Earth has appeared about 1 gigayear after the solar system formed. So stars must live for this long, at least this long, for planet formation, for the formation in the habitable zone to develop life. So here is the lifetime of different mass star A, F, G, K. This time stars survive long, greater than 1 gigayear. So this type of stars are mainly favored to search for planets. OBA stars are too short to support the formation of life, you can say. Another key idea is the stellar radiation. We know the peak spectrum from the Wien's law, that is the peak spectrum of the sun is related to the surface temperature of the sun, and this peaks in the optical. For the Vega, that is the A-type stars, its surface temperature is very high, so its spectrum peaks at the UV. The Barnard star, that is the M-type stars, its surface temperature is less than our sun, and its spectrum peaks at infrared. We know that the UV radiation destroys life, any life. So the very two hot stars, that are the A-type or O-type stars or B-type stars, cannot form life, is unexpected. That is unexpected. If stars are too cold, that is infrared photon cannot power photosynthesis. Lifetime and the spectrum of O-type, B-type and A-type stars, lifetime and the spectrum both imply inhospitable to the life. So as does temperature for the M dwarf type star. Then there are limited range of stellar types around which we can search for if habitable zone exists. There are also further considerations to be taken to search for the habitability. Another is that the stars would be stable permanent star. The star would not show any flaring event, and the varying planetary obliquability. The moon stabilizes Earth's season. Martian tilt varies chaotically. So there the stable parent star, this condition, and the varying planetary obliquity, varying planetary obliquity are the other two key considerations to be taken. Orbital ellipticity is another thing. We want the planet to stay within habitable zone. Low impact rate from the comet should be another key feature of habitability. Gas giant can be useful as the planetary vacuum cleaner. Another idea about habitable zone is the galactic habitable zone. That is the suppose here is a galaxy. It is a very centered region, and this is the outer portion of the galaxy, and this is the middle portion of the galaxy. So too close to center, the higher stellar density, there is higher stellar density. This would increase the planetary system disruption. AGN and the supernova will sterilize the planet. And very outer part from the galaxy's center itself, there will be low metallicity, insufficient heavy element for terrestrial planets to form. We will introduce the galaxies from the next class. We will see how the galaxy what is the galaxy's morphology looks like. So until now you can see this galaxy is a disk. So very closer to the galaxy's center, galaxy's disk region, the planets cannot form because there will be a higher number of stars are inside the galaxy, and there will be planetary system will disrupt due to the supernova effect from the stars, or the effect of the black hole or the core black hole from the galaxy itself. And two distant region from the star two distant region of the galaxy itself, there is low metal content and insufficient heavy elements for terrestrial planets to form. Now another key thing to discuss is the planetary atmosphere. We can put Earth Sun values into the equilibrium temperature, which gives equation of T Earth is equals to 254 Kelvin, that is minus 19 degrees Celsius. Actual solar habitability zone is from about 0.47 to 0.87 astronomical unit, but mean surface temperature of Earth is 15 degrees Celsius. So now why this observation and the calculated value is different? You can say that the difference comes from the greenhouse effect, where the sun's radiation this is because sun's radiation picks in optical our atmosphere where the atmosphere is transparent. Earth radiates an infrared where the various species such as the carbon dioxide, methane, H2O trap heats on its way. Some greenhouse effect is essential for life on our planet. Effect of greenhouse on the habitability zone, or the effect of the greenhouse effect on habitability zone. For Earth, greenhouse effect is mild, reference is 34 Kelvin. Venus is within Sun's habitability zone, but its surface temperature is 740 Kelvin. This difference is due to runaway greenhouse effect. Earth does not suffer this due to the low planet temperature, low Earth temperature, carbon cycling by the plate tectonics yet. Greenhouse effect redefines habitability zone, moves us outward, assuming the atmosphere like Earth. So solar system habitability zone is at about 0.95 to 1.15 A. Here is the idea of the continuous habitability zone, habitable zone, continuous habitable zone, where the luminosity of stars increase with age. Habitable zone migrates outward. Earth has been in continuous habitable zone, but Earth may have only 1 gigayear before the runaway greenhouse effect. We will not discuss this runaway greenhouse effect briefly. If you want to study, you can study it by yourself, or we will study those in some next class if we can complete the courses as per our schedule. And then, yes, there are many topics include here. I have not discussed all this topic very briefly. Sometime I have given some just key given the written the key idea or the main result. I have not why this result is coming, how this result is coming. I am not discussing here. This course is very basic course. We just want to introduce you just the key concept, how the key concepts are, what is the implication of this key concepts, or how the key concepts are derived. This thing has not been discussed or are not within the course outline, our course outline. Another thing for the habitable zone is the atmospheric retention. Obviously, the planets need to keep hold to their atmosphere to be habitable. Molecules from the atmospheres are lost if they have sufficient velocity to escape the planet's gravitational field. We know from our very first physics lecture that the escape velocity depends on the planet's mass and the planet's radius. And we know the gas lost, that is the RMS velocity of the gas particles, is depend how the RMS velocity of gas particle, and this related to the planet's temperature. And gas is lost over time if 10 times V RMS is greater than V escape. And here is the approximate composition of present day terrestrial planets' atmosphere. Venus, Earth, Mars has been compared here. You can see the Earth's pressure is 1 bar, and the Mars has the low pressure and Venus has the higher pressure. And the Venus has more carbon dioxide rich atmosphere, and the Mars is also carbon dioxide rich atmosphere. Venus and Mars both have trace amount of oxygen, nitrogen. For the Mars, there are argon present. Both Venus and the Mars, no methane is present. And the temperature for the Venus, you can see this is about 460 degrees Celsius, and for the Mars it is minus 53 degrees Celsius. Here is the short history of our atmosphere, which says the current atmosphere composition is due to life on Earth. The evolution of this atmosphere is has been happened since the formation of our Earth. So the primordial atmosphere, hydrogen, helium were lost. There were outgassing, mainly volcanoes, mainly carbon dioxide. 3.5 gigayear ago, early single cell ocean based life, that is the cyanobacteria, started oxygenic photosynthesis. Carbon dioxide absorbed, oxygen got emitted, and the carbon got deposited. Over few next gigayears, surface rocks oxidized. Current oxygen levels only reached about 0.5 gigayears ago. Formation of O3, ozone, protect the surface from the UV, and the life lives in the oceans. Another key thing, or the last thing for this discussion, this exoplanet discussion, there is the life sign. The atmospheric changes leave distinct spectral signature. This could be used to identify the inhabited planets. Planetary spectrum holds some signs of life. That is, from the exoplanet spectrum, we can get some signs of life. The spectral shape shows that the temperature of the planet and it is right for water to be liquid. The strong carbon dioxide band shows that we have a planet with an atmosphere. This is the life sign which what we see from our planetary atmosphere. The ozone band. So the ozone band shows the plentiful oxygen probably produced by life, and the spectral feature of water show abundant water indicating a planet with the ocean. So atmospheric from the outside Earth, if you take the spectrum of Earth's atmosphere, you will detect the hydrogen absorption line, carbon dioxide absorption line, ozone absorption line, two types of hydrogen absorption line, and the methane absorption line. This kind of spectral signature will tell that the Earth has the liquid water in its atmosphere, and it has ozone, methane, carbon dioxide also present in atmosphere. For the Venus, you can see the Venus spectra. That's in the Venus spectra you will get the carbon dioxide absorption line, but there are no ozone lines or the methane lines or the water absorption lines present in the Venus's atmosphere. So this just end our today's discussion. In short, we can say we assumed in this lecture that the life must inhabit in the Earth-like surface of Earth-like planets. This was our idea. Our motivation was driven by desire to find the intelligent life similar to us. Simple life may exist in wider range of environment. Subsurface of planets, the planets Mars do host life. Planetary satellites Europa, Titan do they host life. Many exoplanets in many stellar system, and many stellar system in many galaxies. We do not have that answer that if simple life can exist in wider range of environments. We do not know that answer if life can exist, or if life does exist in other environment other than Earth. We have to understand that, and to understand that we try to check what is the definition, the habitable zone for a system, a solar system and a galactic system, so that the life can sustain. We just tried to derive an expression for the equilibrium temperature for the planet under assumption that the stars radiated as a black body, planet is radiating as a black body. We explained why low mass stars are more favorable to host the life-bearing planets than the high mass stars, because the high mass stars die within a giga year. They sometimes have stellar wind, those kind of thing. Also they emit very high energy photons which cannot sustain life. We discussed that the greenhouse effect and its implication for the surface temperature for the planet vary qualitatively, vary not at all in broad sense. We just leave that for you. And then we show how the planetary the greenhouse effect is not discussed in very broad way. We only left that for you. And then we show that how the retention of the planetary atmosphere depends on the ratio between the thermal equilibrium velocity and the escape velocity. And then we discuss the life sign, what we detect in the spectrum of Earth, and what we detect and the spectrum of the Venus, where we only get the detection of carbon dioxide. So now this ends our today's lecture. Anyone have any question? The next lecture, yes, the next lecture will be on tomorrow, and then subsequently I will tomorrow is Monday. Monday at about 9:30 around I will take the next lecture, and then the next after that the lecture will be covered the galaxy. We will introduce galaxy. We will introduce different type of galaxy. We will show you how to search for different type of galaxies image, how to download those. And this galaxies lecture will be around 2 or 3 lectures will be covered in this galaxy segment, and then I will introduce few the Python for astronomy, and then in the last class maybe there will be the evolution of the history of universe. That thing will be discussed. That will be around a 30-minute lecture or so. But after finishing the galaxies, we will go to the landing Python for astronomy and do some of the basic lessons of those are done at different summer school standard. Those are standard lessons for introduction of Python in astronomy. Thank you for yes. Do you have any question? If no question, if anyone have any question, you can. If at this stage you have no question, you can write to me. The email has been shared with the registered participants, and I will try to answer. Yes, there were many questions. One thing, there were many key ideas what we discussed, just not in depth, just in from the upper layer we discussed those ideas. I will tell everyone, if you want to learn more about that topic, you can just Google it or check by yourself. I do not know each of the topic, that is the runaway greenhouse process, those processes very clearly. If you want to learn, I will try to discuss those, or you can just check those by yourself. I just gave you the key ideas or the key terms about the formation of planetary systems. Yes, as these lectures were very vast and this topic is very vast and we have to cover all the modules in this course. So we talk those things from the upper level. We just touch those. We have not went into those topics. Anyone have any question? If no question, then I am ending today's session. Thank you. Thank you for joining. Yes, thank you.